In this video, we'll be talking about a concept in time series called stationarity. Now, stationarity is a very important concept for time series because it kind of tells you when you can use a lot of the models we've been talking about, such as the AR model, the MA model, and so on. That is, these models assume that the time series that you're trying to use them on are stationary. So what we're going to do in this video is first talk about what are the conditions for a time series to be stationary. We'll be looking at how to check for stationarity. And then lastly, we'll look at if a time series is not stationary for whatever reason, what are some tricks you can do to make it stationary so that you can take advantage of these models that we've been talking about. Okay, so as we said in the beginning, we're talking about what makes a time series stationary. There's three criteria here. If you look on the internet, there'll be different definitions slightly, but this is the definition I learned, and I think most definitions include at least these three here. There's different flavors of stationarity like strong and weak, and you can get more into that. We might make future videos on that. But basically, stationarity means that the mean of the time series is constant. The standard deviation, or sigma, of the time series is also constant over all time. And there is no seasonality. So let me write that, seasonality. And we'll be looking at each of these and what happens when they're violated graphically. So what we have here are three time series, and each of them violates one of these criteria. So we'll be looking at which one is violated. I think the best way to tell whether or not something is stationary is look at counter examples. So let's look at time series 1 right here. Now, what can we say about the mean? The mean is constant. It's around this axis right here. We see that it's not going away from the axis or anything like that over time, so its mean is constant. There is no seasonality in here, seasonality being a periodic behavior over time that's predictable. So there's no seasonality here. But the problem is sigma, or the standard deviation, or the volatility, whatever you want to call it, is not constant. Obviously, in the beginning of the time, there's a lot of fluctuation, a lot of standard deviation. Then as time goes on, it kind of dies out. So for that reason, it's violating condition number 2. It's not stationary. Now let's look at time series number 2 here. What do we see here? Well, the standard deviation that we had in the previous one, the issue, is solved. We see that it's not fluctuating any more or any less over time. It's kind of just keeping fluctuating the same amount along this trend here. There's no seasonality. We can't really say there's a periodic pattern over time. But the issue, of course, is that the mean is not constant. For example, if we were to look at just this time chunk here, the mean would be around this black line, the axis right here. But if we look at the chunk from here to here, let's say, the mean has obviously shifted over here. So the mean is shifting over time. And so for that reason, this is not stationary either. Looking at this last time series, number 3, we see that the mean is constant. It's around this black line. Standard deviation is constant. It's fluctuating the same amount along its path. But of course, there is seasonality. And if you didn't know what seasonality was, this is a good example of it, is that there's this periodic sine wave-like behavior over time. So for that reason, this is not stationary. Okay, so these are the three ways that stationarity can be violated. And for a time series to be stationary, it needs to meet all those conditions. Before we go into checking for stationarity, I do want to make a quick, brief discussion into how is stationarity different from white noise. We had a video on white noise, and I think a lot of students get them mixed up. One is actually satisfied if the other is satisfied. So if a time series is white noise, if we guarantee it's white noise, we also know it's stationary. Why? Because the white noise conditions are sort of similar. The standard deviation needs to be constant. There needs to be no seasonality. And the mean needs to be 0, which is a constant. But of course, we can have stationarity be around some other constant. So what I'm basically saying is white noise is stationary. But just because something is stationary doesn't mean it's white noise, because the mean may not be 0 and some other conditions may be violated. Okay, so moving on, how do we check for stationarity? Of course, one is visually. That's what we did in these three charts right here. The second one, we're doing global versus local tests. So that means that if we took the mean of the entire series, like of number 2, for example, the mean looks like it would be around here, this gray line, for example. But if we did local tests, which is, again, looking at little chunks of it, the mean is not the same as the global mean. And it's also not the same as other local means with different time slices. So that's another way to look at it. And you can do this not just for the mean, but also for the standard deviation. You can look at seasonality as well. Of course, these are still not as strong as an actual statistical test, such as number 3, use the augmented Dickey-Fuller test, We're not going to get into the specifics of that in this video. We'll have a separate video dedicated to the augmented Dickey-Fuller test, often abbreviated as the ADF test. But just know that there is a statistical test you can use which outputs some number which you can interpret to tell whether or not something is likely stationary. Now, of course, the last part of this video will be, let's say you run into a time series in the wild that is clearly not stationary. It violates one or more of the conditions above. Is it over? Is it game over? Or can you do something to make your time series stationary? Let's look at one specific case and look at tips you can do in general. So how do you make a time series stationary? Suppose you have a time series which is modeled by y sub t is equal to beta naught plus beta sub 1t plus epsilon t, which means that over time it's a function of the current timestamp, basically a linear function here. This is basically slope plus intercept plus some error. So that's what we see in this graph here. It's basically this linear function, this underlying linear function, plus some noise, maybe some white noise, epsilon sub t. So suppose that y of t is that time series. First question, is this stationary? Well, the standard deviation is pretty constant over time. There's no seasonality, but of course the mean is clearly moving up over time in a linear fashion. Therefore, it's not stationary. But it still seems somewhat predictable, so we shouldn't have a reason to give up. Let's try this one trick. Let's go ahead and create a new series called z sub t, which is simply going to be the difference between consecutive values of y sub t. So basically, if this is timestamp t minus 1 and this is timestamp t, z sub t would be the difference in height between these 2 points, okay? And that's what z sub t is for every single point in time. Now, of course, if we expand z sub t, so we substitute this expression for y sub t here, we substitute this expression with t minus 1 as the index here, we do some simplification, and we eventually get that z sub t, so z at any timestamp t is equal to beta sub 1 plus the difference of epsilon sub t and epsilon sub t minus 1. So what is the expected value? If I took the expectation of z sub t, which is another way of just saying mean, right? This expected value is just mean. That would be beta sub 1, right? Because this is just a constant and it's not affected by the expected value. If we take the expected value of epsilon sub t, then that's going to be 0 because this is assumed to be some kind of normal 0 something process. So it's going to have a mean 0. And for that same reason, epsilon sub t minus 1 being also an independent normal 0 something process is going to have mean 0. So that gives me that the mean of this new time series, z sub t, is simply beta 1. AKA, the mean of this new series is constant. And what is the volatility, standard deviation, of this new series? Variance of z sub t. If I were to take the variance of this guy right here, of course constants don't factor into variance, so we can just ignore that as a variance. This is simply, and these two are independent variables. Epsilon sub t and epsilon sub t minus 1 are independent of each other because the errors are uncorrelated from one point in time to the next. So when I have the sum or difference of some independent random variables, I can simply just take the sum of their variances. The sum, and let's just say that the variance here is something k squared. Of course, the variance of epsilon sub t minus 1 is also going to be k squared because they originate from the same generating process. So I get 2k squared, which again, k being a constant, the variance is constant over time. So we have 2 out of our 3 conditions satisfied for stationarity, and of course if we looked at a plot of z sub t, we're going to see there's no seasonality over time because there was no seasonality in the y sub t series, so seasonality couldn't just emerge from somewhere. So we see that all 3 of our conditions for stationarity are satisfied with this new time series z sub t, which means that we are fair game to use our autoregressive, moving average, ARMA type models on the z sub t series. Do note that z sub t will have one less time point than y sub t because basically, let's say y had 3 members, y1, y2, and y3, then z would only have 2 members. It would be y2 minus y1 and y3 minus y2. So z is a time series with one less data point, but we can do the predictions on z, right? Then if we truly want to get back to the prediction in y, which is what we want, we can simply just undo this operation here. So since we got from y to z by doing a difference in y, we can get from z back to y by just doing the addition from the previous member of the y series. Okay, so that's how you make a time series stationarity in order to use all of the models that we've been talking about. Okay, so that was a brief introduction to stationarity. Of course, we will talk about this ADF test in much, much more detail going forward. But other than that, I hope this helped understand stationarity, and until next time.